So, good morning to everyone. My name is Victoras Yannikopoulos and I'm a student in Pierce. Today, I'm going to present you my project with the title Voyager 1 and 2, the epic journey of the human spirit and the messages in the vast cosmic sea. So, let's get started with the initial idea for the Voyager mission. The initial idea was born in the mid-1960s with the lead of Gary Flandro, that was an engineer and astronautical scientist. So, the material of the Voyagers. Voyager spacecraft, both of them, are made from special design materials, and these materials are chosen for their combination of temperature resistance, radiation shielding, and lightweight properties. Energy source. Voyagers are used radio-stopped thermoelectric generation, such as plutonium-238. For example, here we can see a picture of two scientists that they put that energy in Cassini spacecraft. Voyager construction. Voyager has a distance of 3.66 meters and a weight of 825 kilos. Scientific instruments. Both of Voyagers have the same scientific instrument, such as ultraviolet spectrometer, plasma spectrometer, and cosmic ray system, and more, as you can see. Here we can see a picture of all the scientific instruments of Voyager. Protection for sun radiation. A big question for a lot of people is how Voyagers are protected from sun radiation. The answer is very simple. Voyagers are protected by a shield, and this shield is made from material that combine properties such as temperature resistance, radiation resistance, and lightweight characteristics. The golden record. In the heart of the Voyager, we have the golden record. There are two, and that record contains sounds, music, images, and languages, and messages in many languages. So totally we can understand that they carry our civilization. The launch of Voyager 1 and 2. Voyager 2 was launched on August 20 in 1977, and Voyager 1 was launched after 2 weeks on September 5 in 1977. How Voyager are communicate with Earth? Voyager are communicate with Earth because they used an analog transmission of microwave radio signals, digital data consisting of binary bytes like 0 and 1, such as computers. These signals are transmitted to Earth via NASA Deep Space Network or DSN. Now I'm going to show you a video of Voyager images from the Odyssey. Here you can see Europa and moon of Jupiter. Io, another moon of Jupiter. Ganymede, the biggest moon of Jupiter. Now we're going to see let's continue. I think you'll like the video. So, February 14, 1990. Voyager looked back at Earth at a distance of 3.7 billion miles and took the last picture, the pale blue dot. Let's see video.
This was the pale blue dot. This was our willingness to see the Earth as a one pixel object in a far greater cosmos. It's that humility that science gives us, that weans us from our childhood need to be the center of things. And Voyager gave us that image of the Earth that is so heart-tugging, because you can't look at that image and not think of how fragile our world is, how much we have in common with everyone with whom we share it, our relationship, our relatedness to everyone on this tiny pixel.
Now we're going to talk about the scientific benefits of Voyagers. Voyager 1, such as 2, gave us a lot of scientific benefits, such as that they explored the outer planets, they discovered new moons and future of the planets, examined the magnetosphere of the outer planets, and they offered valuable knowledge about cosmic rays, the composition and the properties of interstellar matter. Here, if we press the first link, we can see the mission status, both of the Voyager. As we can see, here we can see the mission status, Voyager 1 here and Voyager 2. And if we press the second button, we can see the timeline and all the benefits that gave us Voyagers, as you can see. So, now we're going to talk about the development of Voyagers. The development of Voyager is interstellar probe that is going to launch around 2030 with 2035. The interstellar probe is expected to travel at a significantly high speed, approximately 100,000 miles per hour. Here we can see a picture of how maybe it will be interstellar. Let's see a video of how Voyager traveled. Of human curiosity, courage, and hope. You can see dates. When Voyager 1 and Voyager 2 were launched in 1977, they carried with them messages from our planet, embodying humanity's desire to connect with the universe. The golden record aboard the spacecraft is a monument to human creativity and ambition. It contains sounds and music from around the world, greetings in many languages, images of life on Earth, and scientific information about our planet. This message in a bottle reflects the unique and multiculturalism of humanity, showcasing the diversity and beauty of human species. The Voyager mission unites us as a human species, remind us that we are all passengers on the same spaceship, Earth. This mission represents the eternal quest for knowledge and understanding, our desire to explore the unknown and find our place in the universe. The Voyager spacecraft, now the most distant human-made objects, continue to travel through the interstellar space, carrying our messages into unknown realms. They are ambassadors of humanity, points of contact, and reminders of an era when the human spirit dared to reach beyond the sky. This mission embodies the curiosity, perseverance, and hope that characterize us as a species. It is a living example of what we can achieve when we work together, gazing at the stars and seeking the answer to the eternal question, what is out there? So, let's continue. Dr. Stamats Krimizis. I have the opportunity to meet him. It was a lifelong dream come true for me. It was our first encounter and has already become a milestone in my journey. I sincerely thank for the unavailable help and the generous knowledge that you share with me. Kazantzakis once said, reach where you cannot, and Professor has reached where no one else has. With his inspiration, I hope to reach as far as he possibly can. Thank you from my bottom of my heart. So, now I'm gonna read you my message to you. As Voyager continues its lonely journey through space, it reflects the journey of the human race. Just like Voyager started its mission to explore, driven by human curiosity and creativity, we too are on our own journey through time, learning, growing, and exploring. One day, far in the future, Voyager will go silent, its energy gone, drifting forever in the cold darkness of space. This reminds us that everything in the universe has a beginning and an end. Our lives, our civilizations, even our species, just as Voyager's journey will one day end, so to will the story of humanity. But this is not a message of despair. It is a call to action, a reminder of the power we have now. Voyager was a triumph of science and cooperation, showing what we can achieve when we work together. If we, as a global community, embrace science and knowledge, we can shape our future, extending humanity's journey far beyond what we can imagine. Let's invest in science that can heal, innovate, and unite us. Let's protect our fragile planet so it can continue to support life for future generations. While our time is limited, the impact we leave behind can be lasting. The end of Voyager's mission will not be a failure, but a celebration of all it has achieved. Likewise, the end of humanity, whenever it may come, should be a testament to the height we reach and the legacy of knowledge, peace we left behind. In the advances of the universe, we are small, but our dreams, our aspirations, and our ability to create and explore make us extraordinary. Voyager's mission may end, but the legacy of our species can continue to inspire and guide those who came after us. Let us all remember the pale blue dot photograph taken by Voyager, reminder of our place in the universe and how fragile we are. If even one person in this room today decides to put that photograph in their office, in their home, or in their school, it could be a success that will spread everywhere and maybe, just maybe, change our future. If all nations and government place this photograph in their office, our priorities would shift. Let us invest in knowledge and the evolution of human brain, which mirrors the universe with its boundless potential. Let us focus on medicine, physics, and all the science that unite us before Earth can no longer accommodate us. This photograph could be the key to a new beginning, a reminder of our responsibility to the planet and to each other. I want to give many thanks to Dr. Stamats Krimizis, that was my supervisor to all this project, and Dr. Konstantinos Gialinas, that gave me a lot of information about the interstellar probe, Cassini, and all these videos that I saw you. Thank you.
Now I have the great honor, we have the great honor, to have with us Mr. Thanasis Ikonomou, Professor Emeritus, Enrica Fermi Institute, University of Chicago. He will speak, the title of his speech is 60 Years of Exploration of Our Solar System, My Own Experience. Mr. Ikonomou, it's a great honor.
Πώς σας με ακούτε?
Σας ακούμε.
Ναι, σας ακούμε. Ναι, σας ακούμε. Μπορείτε να ξεκινήσετε, κύριε Ikonomou.
Ναι.
Ευχαριστούμε. Ο κύριος Ikonomou, Mr. Ikonomou is one of the greatest astrophysicists from Greece and from USA, of course. And it's a great honor for us to having you here. He is also a Balkan, let's say, citizen that counts the star. That's what he told me when we first met. Mr. Ikonomou, whenever you're ready, please take your time. You may start. You can share your screen if you wish. Just press the share screen button. Okay, have you tried to share your screen? Can you share your screen? Push the button.
Yes.
Okay.
Screen.
We still can see your presentation.
Πρόβλημα υπάρχει πάλι. Share screen, αλλά δεν το βγάζει. Λοιπόν, πάμε από την αρχή γιατί δεν μου το βγάζει. Ναι. Λοιπόν, πάμε από την αρχή πάλι, έτσι. Γιατί περίεργο, περίμενα πρωτήτερα το είχα κάνει shared. Ναι, ναι, αυτό πατάω. Share screen.
Και τα δύο πάνω,
αυτό κάνω, αλλά δεν πηγαίνει στο share screen. Λοιπόν, μια στιγμή λίγο. Αρχίζουμε από την αρχή, βγαίνω έξω και μπαίνω μέσα πάλι, έτσι.
δεν το αλλάξει. Ωραία, γιατί δεν ξαναπείτε αυτό.
Γιατί κάτι... Lift. Τώρα πρέπει να με ακούτε και τώρα πάμε share screen. Ναι, εδώ είναι το πρόβλημα.
Έχει κάποιες επιλογές.
Ναι.
Θα πατήσετε αυτό που είναι όλη την οθόνη. Πατήστε όλη την οθόνη. Κάντε
Screen without physical standpoint, whiteboard, basic. Share. Λοιπόν, ωραία.
ένα πράσινο βελάκι από την κάτω.
I launch the meeting. Are you on screen share?
Όχι. Θα πρέπει να βρείτε το PowerPoint.
PowerPoint.
Και κάντε μεγιστοποιήστε την οθόνη.
Έπρεπε να το ανοίξω όμως το PowerPoint.
Ναι, από πάνω δεξιά κάντε μεγιστοποίηση. Μεγιστοποίηση. Και εμείς σας λέμε και εσείς απλά μεγαλώστε το PowerPoint.
Δεν μου δίνει την αυτό.
Πατάτε πάνω σε ένα εικονίδιο. Πάνω δεξιά, δίπλα στο εκεί, μεγιστοποιήστε την επιφάνεια.
Όχι.
Πατήστε 5. Πατήστε 5.
Περιμένετε, εδώ είναι το...
Εκεί νομίζω και είναι απλά μια εικόνα. Με αυτήν δεν θέλετε το πάρετε. Πατήστε πάνω ένα ποτηράκι που λέει from beginning. Πατήστε εκείνο. From beginning.
Πώς λέει?
Να μεγιστοποιηθεί ο θόρυβος. Αυτό. Όχι.
Αυτό είναι η θάλασσα, δεν είναι το...
Έτσι όπως είναι, λίγο το ψιλοβλέπουμε. Μπορείτε να ξεκινήσετε να θέλετε να φυλάτε, άμα δεν έχει πολύ μεγάλο βίντεο.
Όχι, όχι, πρέπει να το βρούμε αυτό, το control application. Αυτό εδώ πρέπει να είναι, αλλά...
Μια απλά εικόνα από όσο και να τα αλλάξετε, δεν θα πείτε τίποτα. Να πείτε πάνω δεξιά, να μεγιστοποιήσετε την παρουσίαση. Εμείς σας βλέπω σας πούμε κανονικά, αλλά πρέπει να μεγιστοποιήσετε την λίγο πιο πάνω, λίγο πιο πάνω το ληστή. Δείτε από το χείρι.
Εδώ αυτό.
Όχι, όχι. Το έχετε λάθος. Θα πρέπει ο κέρσορας.
Για να κάνω stop sharing, να αρχίσω το PowerPoint.
Κάντε στα ψέντα.
Αρχίσω το PowerPoint. Ωραία.
Ωραία, ξεκινάμε.
Ωραία, εντάξει. Good morning, everyone. I'm sorry for all these technical problems. I am Thanasis Economou, Professor Emeritus at the University of Chicago. And I had the privilege of to participate in numerous space stations by NASA, ESA, Russian and Japanese and British space agencies in space explorations. I'm sorry I cannot be with you today because of some health problems. You see, I was hiking in the mountain and unfortunately I felt and injured badly my knee that required complicated surgery, and the healing takes a much longer time than I expected. Now, as you know, the space exploration started with a simple beep beep. It was coming from the orbit, from the Sputnik 1 that was in orbit, Earth's orbit, on October 4, 1957. And lately, a little later, they have the Soviets, they had another mission with the first man space, Yuri Gagarin was the first cosmonaut to go around the Earth. And the Soviets, they continue to have many other successes in space, like the first missions, lunar missions, the first spacecraft that left Earth, and so on. The Americans were totally unprepared and surprised, but they put a lot of effort and eventually caught up with the Russians and also won this competition of who will be the first to put a man on the surface of the moon. At that time, I was a student at the University of Prague studying nuclear physics. And after I finished my studies, I emigrated to the United States just in time to get in a group at the University of Chicago that was selected by NASA to build instruments to explore the lunar surface. You know, at that time, there was no technology to do any exploration remotely. So all the technology has to be invented from the scratch. One of the main things that we wanted to study about the moon was its surface composition. And there was no instrument that could use remotely. So we selected a method, a nuclear method, that was used in 1911 by British scientist Ernest Rutherford to discover the nucleus of the atom. So what it is involved is having a source of alpha particles bombarding the surface that we want to analyze, and then detect all the scattered alpha particles. And from the number of particles that we can this. I have some interference here. From the number of particles that we can detect is defined by these equations. The number of particles at a certain energy is a function of all the particles coming from the fraction of the atoms in the sample they want to analyze times some initial intensity of the alpha particles. And the energy of the alpha particles over that we measured over the energy, the original energy of the alpha particles is a function of scattered angle and also the atomic mass of the what's in a sample. So these expressions, if we, it turns out that the separation for all the elements is best for 180 degrees. So if you plug into this equation theta equals 100 degrees, you get in the energy that we have measured from the scattered particle over the original energy is just A minus 4 over A plus 4 squared. By knowing now the original is 0 and measuring the energy of alpha particles, we can determine what's what elements are in the sample we want to analyze. So we built an instrument to do just that, that included an radioactive source. In that case was curium-244, and trans uranium element, radioactive element. And here is the detector that detects the scattered alpha particles from sample we want to analyze. In addition, we had several other detectors that detect the protons that are produced in the assembly by alpha P nuclear reactions. Now, this scattering can be from the surface with the maximum energy, but also can be from the alpha particles that penetrate below the surface and they scatter below. So they come with the much less energy. And some of these particles don't even come out. They've just been absorbed in the sample. So our spectra, actually, they're not a single lines, but they are rectangular with the energy, the maximum energy that defines, this each element. For example, for carbon, if you plug into the equations A minus 4 plus A plus 4 squared, you get about 1.25%. To multiply the energy, so you get a quarter of the energy of the original alpha particles. So this is the spectrum for carbon, spectrum for oxygen, for iron, and so on. So this is a picture of our instruments that we built for the lunar missions, called Alpha Scattering Instrument, with 2 alpha detectors, 4 proton detectors, and 6 radioactive sources. This is the spacecraft that we put our instruments in 1967 and sent it to the moon. And this is the instrument sitting on the surface of the moon, analyzing the lunar surface. This is a group of people that were involved with leading Professor Turkovich, our leading person in this group, and electronic engineer, machinists, and mathematicians, and programmer to analyze the data, and a thermal person. This indicates the spectra we obtained from the moon. And I can tell you which elements we can see. We don't see much of the carbon on the moon, but we see lots of oxygen, magnesium, silicon, calcium, and potassium, and iron. From this, and this is the proton spectrum. From this data, we can derive the atomic percentage for each element. So when we got our data and got the composition, it was clear from this data that the moon, it did not have an contrastive carbonate composition that was the prevailing idea at that time that the moon was a body was captured by Earth, and there was a contractious contract. It clearly indicated that there was of basaltic composition, and with us at that time at JPL, when we got the data, was the main proponent of this capture body, that the moon was captured by Earth, Professor Harold Urey, which was very famous, was Nobel, he had Nobel Prize in chemistry in 1934 for discovering the deuterium element. Also, he spent a lot of time in studying the origin of planets and the moon, and he had this idea that the moon was captured, but he graciously accepted our data, and his idea was rejected. We had 3 missions to the moon with our instruments, Surveyor 5, Surveyor 6, and Surveyor 7. This is one of the Surveyor 3 on the surface of the moon, visited by astronauts from Apollo 12 that they brought us back lots of samples from the surface of the moon, and also some of the parts from the surveyor to analyze them and see the effect of being on the moon for more than 3 years. Then after that, follow all the Apollo missions. As you know, there were 12 American astronauts on the surface of the moon, and they studied the moon and brought about 300 kilograms of lunar surface back to Earth to analyze in our laboratories. And we also analyzed, the Apollo 11 returns samples from the moon and compared with our results, and as you can see, there were very similar results. So we were very happy. After that, the space exploration continued with many other missions to different planets, and I was participating in some of these missions. Altogether, I participated in 17 missions from the moon, Mars, comet missions, asteroid missions, with not only NASA, but with Russians, with Japanese and British space agencies, as well as with European Space Agency. Obviously, I cannot talk about all of these missions, so I will limit myself to several missions. So one of the missions it was the Stardust mission to analyze cometary samples in situ and also collect some of this material and bring back to Earth to be studied much better Earth laboratories than we can do in space. So those are the objectives of the mission. The collection, the capsule was built by a Jet Propulsion Laboratory. It's called aerogel collector. And also we wanted to measure the dust intensity and the mass distribution of these dust particles that are coming from cometary nucleus. And this was done by an instrument called Dust Flux Monitor Instrument, was built at the University of Chicago. The typical comet, as you know, consists of the a nucleus, and it has a long tail, which is particles that they are emitted from the comet and scatter the light so we can see the comet. The comet that we selected was Will-2 comet, and the Stardust mission was launched on February 7, 1999, and arrived to the comet on January 2, 2004. Then it returned to Earth on January 15, 2006 with its precious cometary material. This is the instrument we use to detect the dust particles and their mass distribution. Consists of two areas of very thin film that when the dust particles goes through this film, and you connect, these two surfaces of the film to an amplifier, you get a nice electrical signal with the height of which indicates, the size of the particle and so the velocity. And these comets, when we go through, we know the velocity is mostly determined by the velocity of the spacecraft and not the velocity of these dust particles. They are very slow coming out from the comet. So by knowing the velocity of the spacecraft, we can determine the mass of particle and also the size and the numbers. Before the mission, there were models of what we could expect to detect during the missions. And as you can see, the shape is a Gaussian curve centered around the closest approach. And all the activity is within a few minutes before and after the closest approach. And this is exactly what we measured with our instrument. This is a complicated curve showing the number of particles per second. The lightest numbers is in the back and the heaviest is in the front, but all they have this Gaussian curve within the statistics, of course, that we were expecting to see. And here is the moment when I received the data from our instrument and announced this to the group, and then we all were very happy that the instrument worked after being more than 5 years in space. You can imagine how big a relief was it for me, because I didn't know if the instrument would work or not. So this was a very joyful moment. This is the picture that the cameras from Stardust took of the Will-2 spacecraft. It's heavily cratered, and they have lots of pictures, and they have a three-dimensional model of this. So now the spacecraft collected also when we get through the comet, lots of dust particles with this capsule, which is full of compartments containing a material called silica aerogel. And after it collected, it closed, it came back to Earth, and here we are, a jet propulsion laboratory control room on January 15, 2006, waiting for this capsule to land to enter the atmosphere and land on Earth. Here's the schematics of this center. So the spacecraft come back with the capsule. Just before entering the atmosphere, it released the probe containing this silica gel capsule, and which then continues in the atmosphere, and at some point, when the velocity is much lower, parachute is deployed, and very close to the Earth, parachute is separated, and the capsule ends on the surface. It was a night return, so you could see a trace of this, like a meteorite entering the Earth. And here is the probe landed on the surface somewhere in the desert of Utah. It was immediately picked up by the team waiting for it, brought to the laboratories, and then open it. Very careful, and here are all the compartments of silica gel, filled now with dust particles. As you can see, this is the taste of these particles as you enter this material. Silica gel is very thin, low density material, almost a little thicker than the air, actually. So the particles, they go and they lose the velocity, and they're captured. Then these particles are sent to different laboratories around the Earth to be analyzed individually, each particle. Now, as I told you, when the probe entered the atmosphere, they deflected the spacecraft and avoided it to enter the atmosphere and burn, and put it in the orbit around the Earth. It was still, the spacecraft was in very good shape. It has lots of fuel supply, and we were looking to what to do with this, if we can find any target to send it to that to continue the mission. Unfortunately, there was no other comet in the horizon so that we can send the spacecraft until somebody from AGU center, NASA center, figured out that we can send it to another comet, Temple 1 comet that was previously studied by the Deep Impact mission. And what Deep Impact mission did is it bombarded it with a heavy copper body and created a huge crater there. And they wanted to see how much material will come out, what will be the diameter, and so on. But unfortunately, there was so much dust coming out that they could not determine all these parameters. So what we propose to NASA then send this Stardust spacecraft to Templo-1 and continue the observation of the Templo-1 comet. This is the Templo-1 comet, photographed by our cameras. And this was, again, what we measured going through its tail, similar to what we had before, but with different now frequencies, much less activity. Now, this is another photos of the Templo-1 comet, and I want you to try an experiment. Look at this screen and put your finger in front of your nose, about 10 centimeters away from your nose, and focus on the tip of your finger. If you now remove fast your finger, you will see in the middle a three-dimensional picture of this comet. Do you see it? If you're not, try again, but you should be able to see the three-dimensional picture of this comet. Okay, so now let's go to another mission. The Cassini mission. Cassini mission is one of the most successful missions of NASA. It is a joint mission by NASA, ESA, and Italian agencies. It was launched on February 15, 1957, and reached Saturn on July 1, 2004. I was supposed to work for 3 years, but we got several extensions and lasted until September 2015. Cassini mission, it was as I said, the most successful mission, and probably one of the most expensive too. It studied not only the planet Saturn, studied its rings and satellites. It took, I don't know how many hundreds of thousands of pictures. It had 16 instruments on its payload, cameras, UV spectrometers, infrared spectrometers, radar, but it also had one component called the Huygens probe, provided by ESA, that was deployed to the surface of Titan, the biggest satellite of Titan. It discovered that the atmosphere of Titan is mostly nitrogen with some fractions of methane. Also, on the surface, sometimes it's raining methane, And there, like here on Earth, we have water lakes, and on Titan, they have methane lakes. Of course, we did all the measurements with the radar, and they took lots of pictures from the surface of the Titan, mostly frozen water and sometimes methane. This mission, as I said, lasted until September 2017, to the last drop of fuel that was available to control the spacecraft. And in order to prevent any contamination of either of the satellites from Earth living microbes, they decided to send the Cassini spacecraft into Saturnian atmosphere where it burns. One of the instruments on this mission was at the University of Chicago, called the high rate detectors. It was similar to what we have on Stardust, which measured now the microscopic particles of the rings, because what you see on the Saturn are mostly these spectacular rings that are composed with water ice of microscopic size. Also, this instrument was used to prevent the spacecraft from going through areas of the rig where the particles were too large that could destroy the instruments or the spacecraft itself. As I said, during the actually 13 years of operation on the surface, on the orbit of Saturn, the Cassini studied the entire Saturnian system, its spectacular rings, and we also were measuring, the dust on the dust and the water particles on all the rings, based mainly on a ring. One interesting thing or discovery of Cassini was the oceans under the ice of Enceladus spacecraft. See, when we went very close to Enceladus, we observed, the dust around it, but the maximum was not in the equatorial area, but way much closer to the South Pole. And when we were the first to observe this phenomenon, but all the instruments then they look at the data and observe the same thing, So it turns out that on the South Pole are these fissures on the ice, and from these fissures come jets of water, and from this they detect, assume that there are oceans of water under the surface of ice. One other mission was the Rosetta mission in 2004 and 2016. Rosetta mission, it's an ESA mission. It was launched in 2002. Actually, it was scheduled to be launched in 2002, but they missed the launch, and so they missed also the comet they were supposed to launch. And 2 years later, they found another comet, Churyumov-Gerasimenko, which was discovered just recently by two of the Russian scientists, Churyumov and Gerasimenko. I met them both in some meetings. Well, we visited many other comets, Halley by Giotto and Vega in 1986, the Borrelly by Deep Space in 2001, Balkan in 1995, will do with Stardust and Temple in 2005. So this was only all either flybys, but the Rosetta mission was carrying a component of this Phyla that was supposed to land on the surface of the comet and study the comet. So this shows the trajectory from the launch. In order to gain some speed, it had to get gravitational assist from Earth several times and from Mars, and then finally get into the orbit to get the spacecraft way out and to rendezvous with the Churyumov-Gerasimenko's spacecraft. I really have an appreciation for the navigators that designed this mission, the trajectories. Imagine now you launch a spacecraft some place, and you expect after so many orbits and for 10 years later to get into exact position where the comet will be within very limited time. So this happened. The spacecraft got into the orbit of the comet, started to study it, and continuing way after the closest the perihelion. Here are some of the dates that all this happened. Now the Phyla capsule had many instruments. The payload was the cameras, the spectrometers, and I got many useful data from this comet. The APXS was also on the board and was mounted here, and it was supposed to be deployed to the surface after its landing. And here are the team of the APXS instruments, mostly Germans and French, and myself as a POI. This is the instrument that we use for this mission, similar to, and instruments will be developed after the lunar missions, and I will talk about this a little later. This is the picture of the Churyumov-Gerasimenko comet. It's like two comets joined together. It's another picture of it. Here's the how it landed on the moon. It was released from the some height when it was around the comet. The probe continued, and at some point reached here is the picture of approaching the comet. And here we are at the control room in Cologne, Germany, following all these things happening. And after we got the word from the navigators that we have a touchdown, we were very happy, started to celebrate and drink champagne, but we noticed that something strange was happening in the control room. They were looking at the screens and talking among themselves. We asked what's happening, told us that although they got the touchdown signal, it looked like we are still in the air. What really actually happened when the probe touched the comet, there were two systems that were supposed to fix it to the ground, but none of them worked. So what the probe, because there's very little gravity, jumps and continues to be in air for almost an hour and landed completely in different place that it was supposed to land. It was supposed to land here, but when they looked, it was not there. So they started to look around the comet and finally discovered it was in the ditch and landed in the site. So although this mission was very successful from orbiter, and many instruments on lander got the data from this position, I was very disappointed because we could not deploy it to the surface to get the composition, the elemental composition of this comet. Now that let's go to the Mars missions. As I told you, after the lunar missions, we were concentrated for mission to the Mars, but for a long time did not happen much. So we used this time to improve our instrument, and NASA was supporting us to do additional improvements. In 1976, I published a paper called an alpha particle instrument with alpha proton and X-ray modes, which was a much more advanced and much less, much lighter instrument, so much more capable. What I did an additional mode, except the alpha and protons, and X-ray mode. It turns out that our source that we are using to bombard the samples we want to analyze also has X-rays, the L X-rays from this element in the region from 40 to 60 keV. And this indicates that when you bombard the sample either with alpha particles or with the X-rays, you generate additional X-rays, we call it characteristic X-rays, they are indicative of the elements present in the sample. So all I have to do was to put an additional detector to get the additional information from this instrument. And an additional benefit was that in the place where the alpha particle has a problem to separate the heavy elements, the X-ray has no problem to separate nickel from cobalt, from iron, and so on. Where the alpha mode, it cannot separate, and we have to group these elements. And in addition, the alpha is very good separating the light elements, carbon, nitrogen, oxygen, where X-rays cannot detect these elements. So those two modes are very complementary and contributed to the big improvement of the instrument. Here is the X-rays that I'm getting using a laboratory X-ray. So the only problem with this was that the X-ray detector that was available was too heavy, and it needed liquid nitrogen cooling to cool it to the temperature almost minus 200 degrees centigrade. Well, in space, you don't have the liquid nitrogen or, the argon gas that also can be used for cooling. So I had a big problem, and I had to solve this problem. So NASA was for a long time supporting me to discover detectors that will work at room temperature, and we didn't need the liquid nitrogen cooling. So I played with for many years trying to find a new X-ray detectors using the mercuric iodide material, cadmium telluride, cadmium zinc telluride, and finally, we ended up with the silicon PIN the detectors just before the Mars mission, the Pathfinder. Technology company in the United States came up with this silicon PIN detectors that we incorporated into the system that did not require cooling or big volume. So this is the instrument now will be built for the Pathfinder mission. It has, the radioactive sources. Beside here are the alpha and proton detectors, and this is the X-ray mode I'm talking about. That it make a big improvement. It did not have exactly the resolution of the laboratory X-ray instruments, but it was good enough. Later, the industry came up with better detectors that have exactly the same energy resolution as the laboratory instruments. Now, the Mars missions. Mars attracted many nations to have to send missions to Mars, and you can see here how many missions were sent to Mars. More than 50 actually, starting in the 60s with the Soviets and the Americans a little later. But here we are now with the Mars Pathfinder. And the question is why, Mars? Why Mars is so interesting planet? Well, Well, first of all, Mars is the most Earth-like of any terrestrial planet. Yeah. It's the only planet that could support life in future. People are saying, sending astronauts there, people trying to change the climate there so it can be very friendly to the life, but that's very questionable. Earth is the only terrestrial planet has abundant water. Because of that, probably life could initiate on the planet Mars earlier in history, because Mars at that time was completely different planet. It had thick atmosphere, similar to Earth's atmosphere, where now has very little atmosphere. It does not have any water on the surface because the temperature is very cold. It's below 100 degrees centigrade. And also, it's interesting planet if we want to study what happened there and to prevent something to happen in our Earth. And how do we know that Mars was completely different planet in the past? Well, from the orbits, we can take image. You can see there was lots of water activity on the surface of Mars. Those river bays, and there were oceans on the Mars. So in 1990s, U.S. planned the Mars Pathfinder mission to Mars. What was it? It was a lander, and at the last moment they added a little rover called Sojourner with about 15 kilograms. It's a very little gadget, and it had mainly two science instruments. It was, besides the camera, the only other scientific instruments was our alpha proton X-ray spectrometer that developed just in time for these missions. Here we are at Jet Propulsion Laboratory with the Sojourner interfacing our instruments to inside of the electronics of the Sojourner. This is a picture from Cape Kennedy, putting everything together and loading the alpha radioactive sources. Then the entire was put it in the lander and then to the rocket, and 7 months later, launched in July 1996, and 7 months later we are sitting on the surface of Mars. Very successful mission. The rover got off the lander and started to take measurements and analyze Martian rocks. So we're very happy because there were so many rocks to analyze. Those are the spectra, the real spectra from the one of these rocks. And from this spectra, we were able to get very detailed elemental composition of Martian surface and Martian rocks. So after the Spirit and after the Pathfinder, NASA was planning 2 other landers with the rovers, the Spirit and Opportunity. Actually, initially was only 1 rover, but NASA got a little scared that if we lose this, They had two previous failures in 1999 and 2000. So to make sure that one of the spacecraft will make it safely to the Mars surface, they added another rover. So we had Spirit Opportunity, two different missions, exactly the same, at where the launched in 2003 and lasted until 2017. This is the the image of the Spirit and Opportunity were the same. With all the payloads, it was much larger rover, much more powerful payload. This is the cameras and the thermal emissions spectrometers. Except that, we had the robotic arm that contained four other instruments. A microscopic imager to take microscopic images of the surface, the alpha particle X-ray spectrometer, a Mossbauer spectrometer, and a tool that's called rock abrasion tool. We found that from the Pathfinder that all the rocks were covered with a large amount of dust. So to get the real, the genuine composition of the rock, you have to remove this surface dust. So we had an instrument that can actually brush or drill and the surface and make sure that it's again very clean. Those are our surface analysis from this. No, I'm sorry. Those was the Pathfinder. We ended in two different places on Mars, on Meridian and Planum and Gusev crater. And Gusev crater because we thought that this is that's originally a lake, and we will find some sediments to indicate some life in the past, but it didn't happen that way. The Meridian and Planum is because we, from the orbiter, found that there was a lots of hematite, and hematite is always created in presence of water. That's why the sites were selected. Yeah, we are all expecting to land, very anxious before the mission and happy when it landed. But before that, you know, in order to send something to Mars, there are lots of testing, the retesting, make sure that everything works properly under all kind of conditions. It's supported by a big group of scientists here for the Spirit Opportunity. It's about 75 members. But if you include now the Jet Propulsion Laboratory, technical support teams, that's more than 250 people. And actually, somebody count all the people that contribute to such missions, and the number is staggering. More than 2,200 people contribute to any space missions. This is some of the instruments of this. This is the rock abrasion tools. Very useful because it did work and clean the rocks that we analyzed. And you can see here what we're doing, removing the dust or the grind, the surface enough so we can place the APX and Mossbauer spectrometer to get the clean the general analysis. This is now a picture of our APX instrument, the same as on the Pathfinder. But now with much better energy resolution, we can separate all the elements, the same as in the laboratory. So this instrument then became de facto the analytical instrument for all missions to planets and the comets and asteroids. Those are the results from our spectra. You can see that now we can get even the minor elements down to 20 ppm sensitivity. Some of the pictures from the activities on the surface of the Mars by rovers, you can see the wheels, it's coming, taken from the rear cameras, and some activities, like going up into the small mountain here. There are no roads on Mars, so you have to be very careful to select the road to get up to the hill. It takes time, but fortunately we have enough time because the rovers were keeping working properly. Some activities on the surface, we use the wheels to dig and find all kind of material under the surface. Of course, then we put the instruments and analyze, see what is happening here. You can see the differences here. It's one of the craters. We went around and analyzed the walls and down the surface, the bottoms of the crater. You can see nice pictures and materials that falling from. One of the things that we observe on Mars is that there are often very intensive dust storms. And this dust then eventually settles down and covers everything, the rocks and the voltage that our panels that produce the energy, so we have a big problem. Well, we knew about these dust storms from the Pathfinder, but the period that these two rovers were supposed to operate, there was only 90 days. During that period, we didn't expect any storms, so we didn't take any precaution to remove the dust from the solar panels. So it was a danger that such storms will prevent emissions from operating anymore because we will not have any energy. Fortunately for us, on Mars also you have these dust devils, and they're very often because we can observe them and even photograph them. And some of these dust devils, they went through on top of the solar panels and cleaned it clearly, so we could then continue the mission like the problem did not exist. Some of the terrains we have to travel, we have to be very careful because some of the sand dunes come to the dead end, so you have to be very careful to select which path you continue. Some other areas are very sandy and danger that we can sink into the sand. And actually this happened several times with both spirit and opportunity. So when we sent the plan to cover some distance, next time we found out that it was stuck in the sand. So it took us a long time trying to unstuck it from this position. But we succeeded several times, and finally we lost the spirit after 5 years of operation because we could not get it out, put in a position where we'll receive more sunlight in the winter. So next spring we could not restart the rover. So one other mission I want just to mention briefly is mission to Venus. It's called Venera D mission in collaboration with NASA and Roscosmos, the Russian Space Agency. It's called Venera D. Venera is Venus in Russia, and D stands for Dolgozhivущая. It is long-lasting in Russian. Venus is an Earth-sized terrestrial planet that is completely different from both from Mars and from Earth. What happened there is a severe, extreme greenhouse effect that raised the temperature, and we don't know why the atmosphere is so thick. The climatic conditions are horrible. The atmosphere is 100 times more dense than the Earth, and the temperature reaches values 480 and something like that degrees centigrade in the surface of Venus. We want, of course, to understand why this is happening, and we want to know what's the composition of the surface material, what happened to the water that the other planets have, and understand all these processes in order to avoid something to happen in our Earth, you know. So in 2015, NASA and Roscosmos decided to create the joint science definition time, half from Americans and from the universities and NASA centers, and half from the Russian Space Agency and the universities there, to look at the possibility of designing a mission together to Venus, which we called Venera D. You know, I think that as a planet, Venus was somewhat neglected by all the space agencies, just because of the climatic conditions there. And the only one that were very active were the Russians early. From 1960, they were sending missions, but they were failing because they were not properly built to withstand the huge pressure. When they finally measured the pressure and built their landers properly, they were successful in landing on the surface of and operating actually on the surface of Venus. somewhat close to an hour or hour and a half. So it would be nice if we work with Russians to use their experience with landing and provide very powerful payload to get to explore Venus. And that's what we did for almost 4 years. We look into designing a mission based on the Venera spacecraft lander, and also, considered what to do on the surface of Venus and which instruments to select. That some of them will come from other nations than the Russians, and also very important studies of the atmosphere. So during the descent, we were planning to do lots of measurements to decide the composition and the isotopic composition of its atmosphere. And of course, on the surface, we wanted to do a complete atmosphere, to do the mineralogy, measure the seismic activity, and many other studies. We were designed several options when to land 28, 30, 32. Unfortunately, in 2019, we had the COVID, so we stopped getting together. And later, it was the Ukrainian war that completely stopped this work. NASA decided not to follow this anymore. So we produced a very, I would say, detailed report of this mission and provided it to both Roshforgus and the NASA. We don't know what's going to happen if it will, in the future, will decide to work together or not. It will be pity if we will not work together. Here is one of the, I'm giving a lecture to our Russian colleagues for some of the practices that NASA is using in order to coordinate the effort for this mission. And what I want to end my talk by showing you these two beautiful images of our planet as they were seen from astronauts when went to the moon. And since 1997, I claim that the most beautiful place on the universe is our Earth. You cannot find anything more beautiful. And plea that we should do everything we can to preserve it for future generations. Thank you very much.
Thank you, Mr. Economou. Now we have time for a couple of questions, if you please, if it's no problem.
Yes.
Do you want to ask something? Okay, nothing.
I cannot hear you very well.
Can you hear me now? Can you hear me now?
Barely.
Okay. Thank you very much, Mr. Economou, for your beautiful presentation. Thank you very much.
Okay, thank you.
Ten minutes.
Tell me, can you see the mouse here? Huh? Yes.
Can you sit down, please, so we will start? Can you sit down, please? Thank you. Now we have the presentation of Professor Olgitska Kuzmanovska from Kirill and Methodius University of Skopje. The title of the presentation is Electromagnetic Spectrum View to the Universe. Thank you.
Hello, can you hear me? Like you heard, I'm a professor of astrophysics at the State University in Skopje, North Macedonia. And the field of my research is mostly theoretical astrophysics. So I do a lot of mathematics and a lot of programming, but I will not talk about that now. I will talk about observations and spectral analysis. In fact, some of the things you have heard probably, some of the things you know, maybe some will be new, and we will put them in one story. In fact, the basic stuff in astronomy and astrophysics. So the main point of this story is to answer one of the most basic questions in astronomy and astrophysics. And that is, how do we get information from stars and the objects in the universe? How do we know about the properties of the stars? How do we know about the physical conditions in the stellar interiors? So that is the question. And the answer is in the title. Here it is. So the simple answer is through the electromagnetic spectrum, through the electromagnetic radiation or light, as it is called in English, that we get from the stars. Electromagnetic radiation is a special form of matter. Sometimes we say that it is consisted of small particles that we call photons. Sometimes we say it is consisted of waves. These photons can form only in one way, in the cores, in the bellies of the stars. After they leave their surfaces, they travel huge distances, mostly through vacuum, through empty space. At the end, they come to Earth, and here we have to catch them, we have to register them, and we have to analyze them. So this is, in fact, the main task, let's say, of astrophysics. So these are the three questions that I will talk about. In what form do we get information from the stars and other objects in the universe? What are the means and instruments? What are the ways that we use in order to get that information? And just shortly, I will mention how we process and how we analyze and how we interpret that information. But before I start, I will tell one, let's say, disadvantage of astronomy and astrophysics. And that is that we cannot create the physical processes that happen in stars, we cannot create them in laboratories. It is not possible. So there is no experimental astrophysics. There is no experimental astronomy. We only have the electromagnetic radiation in order to find out something about these distant objects in the universe. So let's see what is the electromagnetic radiation. Maybe some of you know, but I will just put here the basic facts. Like I said, it's a special form of matter, and we sometimes say that we consider that it is consisted of subatomic particles that we call photons. They all have their energies. But sometimes we analyze the radiation like it is consisted of waves. And all waves have their wavelengths and have their frequencies. You can see here. Tell me, can you see the mouse? Yes. So here is the wavelength and here is the frequency, and they are related via this formula. In fact, in this relation, we have the speed of light, the high speed in the universe that photons travel with through the empty space. It's around 300,000 kilometers per second. So as you can see here, tell me if you can't see the mouse, I don't know. Can you see it? No. Aha, here it is. So the wavelength and the frequency are, in fact, not proportional, but they are contradependent, let's say. So if we have longer wavelengths, we have shorter frequencies. If we have shorter wavelengths, we have longer frequencies. And radiation is consisted of many of these waves. If we consider them separately, we talk about monochromatic radiation. If we consider them together, like a mix of waves, then we have continuum of waves. And that continuum, in fact, forms the electromagnetic spectrum. And this simple illustration shows this electromagnetic spectrum that we also get from the stars in its whole. So let's start just to see. Okay, here's the mouse. So if we start from the left side, we have longer waves that we call radio waves. They have smaller frequencies and they have smaller energies. This is how the energy is connected with the frequency. Down, you can see. So the radio waves, long waves with small energies. You know what radio waves are. We all communicate via radio waves. Your telephones work on radio waves in order to transfer information. Then the next, on the right, you have microwaves. They are also radio waves. When we go toward the right side of the spectrum, we go to shorter waves, shorter wavelengths, but bigger energies and bigger frequencies. So we have infrared light, we have infrared light and then visible light. This part of the spectrum we call visible spectrum. Why? Because we have organs to register this part, that are our eyes. So we register we see just small part of the electromagnetic spectrum. And that is the optical part or visible part, we call it. I will talk about it more later. When we go to the right, then we go through to short waves. We have ultraviolet part, ultraviolet waves, and at the end, X and gamma rays, the most dangerous ones. You know them. We cannot see them, we cannot feel them, but our bodies feel them, and they will be damaged if we are exposed a lot to X and gamma rays, you know, in nuclear plants, for example, just to mention one thing. So this is the electromagnetic continuum or spectrum in whole, from radio waves, then infrared, visible, ultraviolet, X, and gamma rays. And what is important for the stars is that these waves are radiated in some relation with the temperature of the object that creates them. So if the object is hot, it creates waves with bigger energies, gamma and X-rays. If it is cool, if it is cold, it creates those waves with smaller energies, for example, radio waves or infrared waves. And you can see that in this formula here. And that is important for the stars. So they create different waves depending what their temperature is, mostly their surface temperature. Okay, let's see a little bit more this part of the spectrum. You can see this small band. That is the visible light, optical part. That is all we can see. It goes from around 380 nanometers till 700 nanometers approximately. And we see it like colors. So short waves are related with blue color. And then we have ultraviolet, then in fact not ultraviolet, just violet, then green, yellow, and so on, toward red color, which has longest waves, in fact. But this is very small, let's say, difference. And that is all we can see. That is all we are equipped with. We cannot see the other parts of the spectrum. Remember that. All we can see, we see just in this small, visible, optical part of the spectrum. So let's see how, in fact, the radiation is formed. Like I said, it is formed in the cores of the stars, just in their centers. This is an optical image of the sun. You know it, you saw a lot of these images. And it is in fact, let's say, consisted of gas, but it is not really gas. This special form of matter that all stars are formed of is called plasma. So it is not liquid, it is not solid, it is not really gaseous, it's plasma. It's material under very high pressures and temperatures. Plasma is consisted of neutral atoms and molecules, but also of charged particles, electrons and ions. And because we know stars rotate around their axis, it means these charged particles also rotate, and they are in fact, let's say, they create the magnetic field of the stars. As for radiation, it is not formed in the whole interior of the stars. It is only formed in the core. Why? Because we have highest temperatures in the core. For example, for the sun is around 15 million degrees. So under these very high temperatures and pressures, nuclear processes start to occur. Only in the stars, nowhere else. In nature, of course, I'm talking about nature. So when nuclear processes occur, we call them thermonuclear processes because they depend on the temperature. When they occur, simply said, lighter elements transform into higher elements. For example, for the case of our sun, hydrogen transforms into helium. I will not go further. In fact, these processes are complicated. But we have lighter elements that transform to heavier elements. And in these processes, electromagnetic radiation is formed and it is released. The continuum, in fact, is formed. The picture down here that you see, in fact, shows how the pressure of that radiation keeps the star stable. Maybe some of my colleagues showed that in another way. So we have pressure of the radiation. We have gas pressure, plasma pressure, that are pointed toward the surface of the star. And they balance the influence, the gravitational force. Gravitational force is, in fact, always directed, to the centers of the objects. Gravitational force always tries to shrink, to collapse the object. And because this radiation is released, in fact, that force is balanced, and we have star with stable radius and with stable mass. So, in fact, the pressure of this light of these photons keeps the star together, let's say like that. You can see here the core. Here is the core. The radiation is formed. You can see how it looks, just in the optical part, of course. We cannot see it in other, but it looks like continuum of waves, all waves next to another in terms of wavelengths. When it leaves the surface of the core, what happens to this radiation? So we are here. We are not at the surface of the star. We are here now. This radiation, this continuum of waves, goes through a long, long journey toward the surface of the star. For example, what is that long? For the sun, it takes around 1 million years of the radiation to come from the core to the surface. So what you see here, what comes here through our windows and reflects so we can see each other, is formed around 1 million years ago in the core of our sun. After it leaves the surface, it takes around 8 light minutes because it moves with speed of light, 300,000 kilometers per second. So it takes 8 minutes to come from surface to us, but 1 million years from the core to the surface. And on this long journey, the radiation changes, the spectrum changes. It changes because it is in interaction with the gas, with the plasma. So it is changed by the plasma, but also it changes the stellar material. So there is mutual interaction, very complicated processes. And when it comes to the surface, it looks like this. Continuum with this dark holes, dark bands that are called absorption lines. It is in fact part of the spectrum that is absorbed by the stellar material. I will talk about the positions. There are strict positions here that are related with the chemical composition of the star. But you can see this continuum spectrum looks like this on the surface. For all stars, it looks similar to this. And we call it absorption spectrum. I will show you that later. And just to mention here, the intensity of this radiation, the flux of the radiation, which depends on R, here the radius, is in fact related, and we can estimate with it, with this formula, the mean, the average temperature on the surface of the star, or we call it effective temperature. So this radiation, in fact, is used to estimate the effective temperature at the surface of the star, which is smaller than in the center. For example, 6,500 degrees is on the surface for the sun and millions in the center. The same thing here, just to precise again, continuous spectrum that goes through the, here it is called atmosphere, in fact that are these exterior layers of the sun, and we have absorption spectrum that travels to our Earth, and we have here to catch it and to analyze it, to see what we can extract from it, what information we can get from it. So in fact, there are three kinds of spectra in the universe, mostly, of course, three kinds, these three types. First, we have continuous spectrum on the left. On the graphs down, you have the intensities that are related with the wavelengths. It is formed strictly in hot, dense matter in the center of the stars. Then we have absorption spectrum, changed now, after it goes through the stellar material. And the third kind of spectra, I will just mention it, nothing else. It is emission spectrum. And it is formed not of absorption lines, not of dark bands, but of these light emission lines. It is formed when the radiation from the stars goes through large molecular clouds. We call them nebula. So somehow it is changed. I will not talk about that. And we have emission lines. But here we are interested mostly in this third, the right side, absorption spectrum. Again, just to remember. So continuous spectrum in the core, absorption at the surface, and you can see these emission lines here from nebula, from large molecular clouds. So what can we know immediately about the stars from this spectrum? Immediately. Yes? The effective temperatures, I told you that. Yes, the effective temperatures. Okay, I will show you. So, first we can estimate the effective temperatures, the mean average temperatures. We use the Planck's law. I don't know if you have heard of it. It is one of the main laws in atomic physics. It was mentioned somehow in the previous lectures. It is connected with approximation of black body and so on. But I will not bother you with that. So I will just say that Planck's law, in fact, relates the flux, the intensity of the light, with the wavelengths. You can see here. And the peaks here of these different curves, these are for different stars, let's say, in fact, are related with the mean effective temperatures at the surface of the stars. So this curve is for star which is hot, 5,500 kelvins, and this is for the coolest star. And what does it mean? It means that with a simple, not very simple, but from classic law of atomic physics, we in fact can estimate the effective temperature of the stars. And if that peaks are in the visible part of the spectrum, in the part that we know of, then we see the stars in different colors. You can see there, these are stars with different colors. For example, hot stars are white, blue. Those that are cooler are, you know, yellow. Our sun is yellow. And the coolest stars are, in fact, reddish. And we can see that with telescopes. Of course, if the peaks of these Planck curves are in the optical part of the spectrum. The other thing we can know is the chemical composition of the star. How? According to the position of these bands. So these bands, these absorption lines, have exact positions. If we relate them with laboratory standards, with emission lines from different chemical elements at laboratory, according to the position, you can see here from sodium, according to the position of these dark absorption lines, we can say what is the chemical composition of the star. For example, this is optical part of the spectrum of the sun. You can see here calcium, hydrogen, iron, magnesium, and so on and so on. So we can estimate the chemical composition of the stars just according to the position of the absorption lines in the absorption spectrum. Left, you can see different absorption spectra of most bright stars. So the position of the absorption lines is different, but they all look similar. Also here, intensity via wavelength. So these dark holes are in fact absorption lines. And I, again, will remind you, that is all we can get from the star. Here is, again, absorption spectrum in its whole. So there is noise, there is everything else. Yes, just to finish, and you will ask me. So there is noise and anything else. We have to analyze it. That is, in fact, the task now. We have to make interpretation. And that is the task of theoretical physics. That is what I do in my scientific work. In fact, we solve numerical equations, numerically differential equations in order to see what is the state of the plasma, in order to find out, to extract all the interactions between the light and the stellar gas. And we do that only theoretically, analytically, or numerically with programming. Yes, do you want to ask me something? Aha, okay. So this is the complicated part, but I will not talk about that, otherwise I will just show you equations and nothing else, and results of programming. I will talk about observations. So I will talk about the first obstacle we have in order to register this spectrum. That is the Earth's atmosphere. You know that we live at the bottom of a huge ocean of gases that we call Earth's atmosphere. These gases change the light from the stars. They can scatter it, they can do other things, but mostly they absorb it. So here at this graph, you can see the solar spectrum. This blue curve is before it enters the Earth's atmosphere, and this is after it enters it and we register it on the bottom of the atmosphere, of the surface of the Earth. So you can see that most part of the spectrum are absorbed. They are absorbed because there is interaction between the gases, this mixture of gases that our atmosphere is consisted of, and the radiation. For example, you can see all the ozone here, or water vapor, or carbon dioxide, and so on and so on. So that is a big problem for astronomers. I will show you how big it is. And you know it. We just here create a story. You know most of these things. So this is what happens with the spectrum when it enters the atmosphere. Let's talk about the good stuff. So we have two windows. What goes through so we can register it? The optical window. all of the visual part of the spectrum. Maybe that is why our eyes are created to register optical light, because it goes to the surface of the Earth. Who knows? And the other part is radio window. Most, not all, but most of the radio waves. The other parts of the spectrum are absorbed when they enter the atmosphere. Now, good things is that, let me just find the mouse. So, the gamma and X-rays are absorbed. That is good for the life on our planet. It is not good for astronauts, but that is why they carry those heavy suits with them, because of the influence of the gamma and X-rays. But they don't enter the Earth's surface. Then most of the ultraviolet light is absorbed. Now, not so much. You all know about that. Why not so much? Now, yes. Tell me. Yes? Yes, because in fact we polluted the atmosphere, you know. We released more carbon dioxide than it was usual, so now the ozone layer is destroyed, and now more ultraviolet rays come to the surface, and that is why we protect now with sunscreens and everything. It was not like this 30 years ago, for example, when I was young. So now, but that is another story. Now we have more ultraviolet light, but still some of it is transmitted on the surface, not all. We still have to go up in order to register it. Then infrared, also absorbed, and these long radio waves. And that is all that we can get on the surface of the Earth. And that was, of course, these obstacles were overcome in decades of space exploration. So let's start with observations, with catching the light. For centuries, for thousands of years, we humans observed just the visible part of the spectrum, the optical part. You can see it there. So the image of the sky we see is in fact optical image. You can see here the sky full of stars. You can see the Milky Way in the center, the most dense part of our galaxy. So it is all in the optical part of the spectrum. That is all we can see. It means that if, for example, we had eyes for different kinds of waves, the picture, the image would be different. So it is not absolute image, no way. It is just optical image. And that is all we had. We observed with naked eye, we call it. For example, this part, look at this image. This is optical image of a part of a sky. It is black and white because it was taken in the beginning of the 20th century. That is why it is black and white. This is what we see. But if we had eyes, for example, for radio waves, we would see different things. All these images are in fact images of the same part of the sky, but in different wavelengths of radio spectrum. So we would see different things. You will see that, how we would see different things if we could register another waves than the visible waves. But of course, we have instruments now for that. That is another story. So just a little bit about the beginning of the observations. Do you know who these people are? These are, in fact, astronomers of Babylon, about 3,000 years ago. So it is considered that around 2,000 years BC, the first records of systematic astronomical observations, you can see them down on these clays, were made. So these are, in fact, Assyrian, Mesopotamian astronomers who are looking at the sky just with their eyes. This instrument that this man holds, in fact, measures the positions of the star, nothing else. But they were following the positions of the stars and objects and made the first maps. Then through ancient times, at the left, you can see Egyptian astronomer, for example, that also looks at the sky. And then through Middle Ages. I don't know if you know, but maybe you watch, serious films. So in the Middle Ages were dark ages in scientific sense in Europe. But it is thanks to Arab astronomers who in fact developed and transferred the astronomical knowledge to modern times that astronomy was observed like science, of course. And that is why, in respect to Arab astronomers, in their honor, still most of the brightest stars on our sky have Arabic names. For example, Mintaka, Arcturus, Algol, so on and so on. Those are Arabic names. So, everything was observed with the naked eye, just the optical part of the spectrum, and you know when something changed. Then we had magnification. So, we have magnification of the images of the stars. Still, optical view of the stars. You know, you heard about Galilei, who first used the lenses that were invented a few decades before his time by Dutch opticians. So lenses were first used, you know, for what? For monoculars. You know, pirates and sailors used them. And then, in fact, first Galileo pointed them on the sky and saw the magnified, 30 times magnified image of some objects, of planets. And you see in this image, he was the first man who saw the 4 largest satellites of Jupiter. You saw them in some previous lectures. Ganymede, Callisto, Europa, and Io. And on these images below, you know this man, do you recognize him? Yes, tell me, just tell. Yes, Isaac Newton. So why do I show him here? Because he was using a telescope which was a little bit different from Galileo's. In fact, his telescope was not using lenses, but it was using mirrors. And of course, you know this, there is this main division on telescopes on refractors that refract light. They use lenses, and reflectors that use mirrors. Most of the telescopes now are those that use mirrors because they can be constructed more precisely than lenses. And just to show you, of course, this list is changeable. The biggest and most important optical telescopes on Hawaii, on Chile, on mountains Subaru and Paranal. The diameter of the mirror is around 8 meters. Then in Arizona, combined telescopes above, which create an effect and magnificate like a telescope with 11 meters diameter. Then on Canarian Islands, we have 36 mirrors combined. And these famous twin telescopes, Keck telescopes. But of course, others are created. Maybe now the list is different. I will return now to Sir Isaac Newton. He is very important for the birth of astrophysics and spectral analysis. Why? Because he was the first man who divided the white light in waves in different colors. You know that this light that comes from the sun is in fact mixture of different wavelengths, different colors. We can see that it is a mixture on one natural phenomenon, rainbows, you know, after rain. But Sir Isaac Newton was the first one who, in fact, put this white light through this instrument that is called optical prism, and that refracts these colors, these waves, in different waves. And he saw first artificially made colors of the visual part, of the optical part of the spectrum. And that was very important. Why? Because you can see here, our eyes are not ideal. They don't see all the colors the same. So this curve here, again I lost it, but you can see this curve with the eye, you know, like this. So it is the spectral sensitivity of our eyes. We are less sensible to blue lights, to red lights. We are more sensitive to green and yellow, and that is why green and yellow especially is prominent to us, because that is the spectral sensibility of our eyes. So we need instruments that will detect spectra like they really are, not just our eyes. For example, this is how it looks, the optical part of the solar spectrum, and this is how we see it. This is how we see it. So this division of color, in fact, went to development of spectral analysis. So we had catching the light, then magnification, and now keeping the light. Spectral analysis method, the analysis of spectrum, was developed around at the middle of 19th century by one chemist and the other Kirchhoffist physicist, and it marked the birth of astrophysics. In fact, it is related with the construction of devices that we know about. Those are photographs, in fact, with the invention of photography. Of course, not this kind of photographs that you have in your mobile phones, because they use some other, they are electronic devices. But these photographs, I don't know if you have seen them. Maybe your grandparents had them, or parents. So they use films. Have you seen these films? So these films, in fact, are now are films, but at the first they were photographic plates. And these plates and films are covered with photographic emulsion, some mixture of substances. And when the light enters, what happens? Some chemical reactions, and then image is formed via this chemical reaction. This is the simplest way to explain how the photography works, in fact. And it was used to photograph the stars, to catch the stellar spectra, in fact. It was used for that. So now spectra were first, let's say, collected. That is a cumulative effect, so more and more radiation was collected. And then they were kept and displayed for later analysis. And this later analysis means that the first catalogs of stars were produced. One of the most famous in 19th century is this Henry Draper catalog. It contains around 225,000 stars, and it was a huge amount of work. To collect all these spectra of all these stars, it was done by a group of women. You can see them here. This is a photograph, the same method like for the stars. And of course, like it was at that time, this was the main guy. It has to be some guy. Professor Edward Pickering, who was in charge for the project. So this is in fact the first catalog, and you can see here, I found this image of one of the first spectra here. The spectra of the star Vega, it is summer star in constellation of Swan of Deneb. And what now we can know if we keep this spectra? First of all, we can classify the stars in different classes according to their temperatures. I told you something about that. From classes O, B, A, hottest stars, blue, white, and so on. Then class G, so our sun is in class G, class K, and at the end, coolest stars are in class M. And these are, in fact, the spectra of these stars. So different absorption lines, which coincide with different elements. And after this invention of photography that was used, different complicated instruments were also created. Photomultiplicators, they are in fact all the electronic devices that use some kind of electric currents. Then filters were used for specific range of wavelengths to catch specific range of wavelengths. CCT devices, and they all transformed the radiation through filters into electric signal. And that electric signal can be kept and later analyzed. And that is all that was done for optical part of the spectrum. And now we go to radio part, to radio waves. Invention of radio telescopes, developing different view. Their construction was related again with the construction of devices that we all know of, that are radio devices. On the left you have this archaic vintage radio device. They were constructed before the Second World War, and in fact with them the first radio signals from the universe were catched. For example, the engineer called Jansky in 1930s detected galactic radio noise, in fact the noise from the center of our galaxy. You can see it is on the wavelength of 14.6 meters. But the birth of radio astronomy, in fact, is connected with some theoretical work done after World War II. Why I mention this war? Because the construction of radio telescope is related with these instruments that were also used and invented in the Second World War. They are called radars. You know what is radars, are you? You know radar? What is radar? So the radars are in fact used to detect airplanes. They are still used in aviation. So they emit radio waves, they reflect from the airplanes and then go back to the radar, so the position of the airplane can be in fact detected. And that is good because these radars were used in the British Islands in order to see the German planes that were bombarding London. So in order to, let's say, foresee the German attacks. But all in all, because of these radars, in fact, the radio telescopes were constructed, and you saw some of them. So, for example, this is, I think, the biggest one in China. So its diameter of this mirror, its mirror is around 500 meters, half a kilometer. Why so big mirrors? Because radio waves have small frequencies. So we need big mirrors in order to enhance the cumulative effect, in order to catch them. And these are some other ones. For example, this is the sweetest one, Arecibo in Puerto Rico. Unfortunately, it was destroyed in hurricane 4 years ago. Then at Max Planck Institute, this is in Russia. So they all have mirrors and these antennas are then used to transfer the signal to computers, where this signal is transported into images. Of course, we cannot see the images immediately. And here is just to make a difference. For example, you have radio image of Jupiter. You can see it up. And optical image. So this is how in radio part of the spectrum Jupiter looks. Or optical image of the sun, and this is the radio image of the sun, totally different. For example, this faint thing here is a galaxy, very faint in optical part of the spectrum. But if we analyze the radio image of the galaxy, we can see that it contains these big jets of material that is, let's say, ejected from their centers, which contain supermassive black holes. And these jets emit only in radio part of the spectrum. So we have totally different view when we analyze the radio part. Some other radio images of different active galaxies that contain these jets that have active cores, active nuclei. And I will just mention here, okay, I will skip this. I will just mention here that the radio waves can be formed also in another way. Not just because of the big temperatures in the cores of the star as a part of continuum. They can be formed with a mechanism that is called synchrotron radiation. What does it mean? It means that when a charged particle enters a magnetic field and that charged particle is moving in straight line, the magnetic field in fact, influences it, and it becomes to move in spiral, in curve, maybe sometimes in, let's say, circle. And because of that circle, we have centripetal acceleration and so on, radiation is emitted. So it is not connected with the temperature of the stars. And we have strong magnetic fields somewhere in the universe. That's a long story. So now we have also synchrotron non-thermal radiation, which is also in radio part of the spectrum. And of course, in order to catch the other parts of the spectrum, we had to wait for the launch of the first satellites. You saw Sputnik 1, and this is Sputnik 2. Do you know who the passenger here is? Laika, yes, the dog, stray dog from Moscow streets called Laika. Fortunately, came back, although I think it died shortly after it came back to the Earth. So the launch of these satellites also enabled the development of space telescopes, the telescopes that we will show in outer space, outside of our atmosphere, in order to catch another parts of the spectrum. For example, ultraviolet radiation, I put here the first one. These are the ultraviolet images of different galaxies. Of course, we don't see here ultraviolet light. Ultraviolet light is transformed in optical image in order to see them in computers. We can only register signals, but we can transform them then in order to get the shape of these galaxies. And most important space telescope for development of, or for registering these other parts of the spectrum rather than radio and optical is Hubble. You know Hubble, huh? Yes, it was launched in 1990, and you can see it range. So it sees optical, ultraviolet, and some small part of infrared light. So not just optical light. It made a huge evolution in development of astrophysics. For example, here you can see planet Saturn, and you can see aurora. You heard about northern lights, aurora, but now you have auroras also on Saturn, because charged particles from the sun interact with the particles on the planets on the Saturn's atmosphere. Up there you can see Sombrero galaxy, first seen by Hubble. Here is in fact a system of two stars, double stars, that let's say eject these clouds of gas. So these are big stars, and these clouds of gas are caught mostly in infrared light of Hubble. And this is one of the most famous images of Hubble. Have you seen it? How it is called? It is called Cradle of Creation. Hmm? Yes? Yes, Cradle of Creation. So why Cradle of Creation? It is located in Eagle Nebula. It is called Eagle Nebula. This large molecular cloud where this picture was taken is called Eagle Nebula. Because here, first, it was the first time that we saw birth of new stars. So these pillars are in fact baby stars. All stars formed in these cold molecular clouds that can exist for millions, even billions of years until some event happens. So they start to fragment. And gravitational force acts in that way that fragments are created. And from these fragments, the stars are created. They shrink, until in their centers, the temperature is so high that nuclear processes start to occur. So these are, in fact, the births or small fetuses, let's say, of stars. And this is the form star. So it is larger. Of course, invisible you can see in infrared. And this is another famous image. Do you know it? It is called Hubble Deep Field. So all these here dots are not stars. These are galaxies. We have big focus. in very large distances and also in the past. So all here that you can see are hundreds of galaxies, and all they contain millions and millions of stars. So in fact, Hubble first saw in the past. Why in the past? Because it takes 300,000 kilometers per second for the light to travel through the universe. So if some galaxy is 40 million light years away, it means it took the light 40 million years to come to us. So we can see that galaxy, how it looked 40 million years ago. And when some object is very distant, we can see it in the past. So let's say when we look at the sky, we also look at the past of our universe, because a light has finite speed, finite velocity. Then, of course, the first space telescopes for X-rays, for catching X-rays, were created. Here is Chandra, the most famous one. You can see here that it can look 10 billion light years in the past or away. Similar thing, in the past or away. And you can see here how Chandra was important for, let's say, development, for knowing the evolution of the stars. Here, you can see here optical image of a large cloud that we call Crab Nebula. It is supernova remnant, explosive process where massive star dies. And the stellar exteriors, its atmosphere is dissipated into the space. And this is what we can see. But Chandra X-ray telescopes can see something else. They can see in the center of this nebula and see the remnant of the core of the star, which does not explode. It implodes. It shrinks, implodes, and collapses and creates one of the most exotic objects in our universe. Not black holes, you've heard about that, but neutron stars. For example, 1 cubic centimeter of neutron star has a mass of millions of tons. We cannot imagine that. So the core of big stars, in fact, shrink and form neutron stars, and here is the neutron star, the remnant of the core in the center of Crab Nebula. We could see it only by this X-ray image. Again, different images of Crab Nebula in different wavelengths. Here is the neutron star. You can see that it rotates with very, very high speeds. And it has very large magnetic field, and it also radiates X-rays and also charged particles on this X. And this, in fact, rays, this high energy jets, it is written here, we detect. But because the star rotates, we detect them like pulses, just, in some periods of time. And that is why these neutron stars are usually called pulsars, when we can catch, in fact, their light. Again, totally different images of the same thing. Here is X-rays, infrared. You can see how it looks in infrared, ultraviolet, the Crab Nebula, this supernova remnant. And gamma rays. Here, in fact, these high-energy gamma rays. Another images, for example, supernova remnant. This is quasar, one of the oldest objects in our universe. They are very, very far away, 10 billion years and so. So these are all X images. And at the end, we have detection of gamma rays. We cannot use mirrors for them. Why? Because gamma rays cannot reflect from mirrors. They have such a small wavelengths that they are absorbed by mirrors. So we have to use this atomic process, in fact, to construct telescopes and instruments that use this atomic process where gamma photon then hits the target, and then it creates pair of particles of matter and antimatter, electron and positron. I will go no further into that. So another method for detecting gamma rays. First, gamma telescopes. For example, these are images of our Earth in different gamma wavelengths. The great observatories, Chandra, Hubble, Spitzer is for infrared light, and Compton is for gamma rays. Again, here the sun in different wavelengths: infrared, optical, ultraviolet, and X-ray. From pictures from different telescopes that detect different parts of the spectrum. Multiple wavelengths of Andromeda galaxy. Andromeda galaxy is the galaxy that is similar to ours, our neighbor, in fact. It's a stellar galaxy that is around 2 million light years away. But we can see it on the sky, not in towns, in cities, but on mountains and on sea. We can see Andromeda galaxy. So we see how it looked 2 million years ago, because it took the light to come to us just 2 million years. Different images with different telescopes of spiral galaxies, Spitzer, Hubble, Chandra. Then gamma images of our Milky Way. And at the end, just to finish with the most famous telescope at the moment, James Webb Telescope, Space Telescope, you've heard of it. It was launched 3-4 years ago. You can see its range here, infrared light. This is the range of Hubble, and this is the range of Spitzer. So here, James Webb, in fact, detects mostly cool radiation, cool objects and parts of the universe. It has the most sophisticated mirror ever made on Earth. So you can see its resolution, Hubble deep field, and now the same image, the deep field, but taken with James Webb Telescope. Saturn, for example. Here is Titan. You've heard of Titan in the previous lecture. So the biggest satellite, it reflects around 70% of the light of the sun. Then Tarantula Nebula. It is very wide, very huge, around 400 million light years. So here you have this image of stars that are newborn, first time seen with James Webb. Exoplanet, a planet around another star, also taken in infrared light from James Webb. Phantom galaxy, very prominent, huge spiral arms, like our galaxy, Milky Way. Then this is the image of Jupiter. Again, auroras. You can see them on north and on southern pole. Of course, these infrared images are, again, I emphasize this, transformed into optical images. Then this is Cartwheel Galaxy. It is with these are companions, with two companions, in fact. It is formed by collision of two galaxies. But when we say collision, you heard about collision of galaxies. Collision of galaxies is not explosive or dramatic process. There is no collision of stars because most of the space in the galaxies is empty. So what collide are molecular clouds, but they are not very dense, so nothing spectacular happens. Just we have matter that is more dense in time. Again, pillars of creation now with James Webb. This is quintet of galaxies. These four here interact with each other. Then planetary nebula. Do you know what is planetary nebula? Huh? This is Saturn ring, yes? Yes, that's correct. So it is in fact a remnant of the outer layers of the star. But the star that has a mass that is less than 1.4 solar masses. So our sun will die like this. its outer layers will just dissipate into the space. There will be no big explosion or anything else. They will just dissipate, and in the center here, a white dwarf will form. And at the end, just to show you here, the selfie of the primary mirror of James Webb Telescope. It was taken with the secondary mirror. So that was it, what I planned. Thank you.
Is there any questions?
Yes, I know you're hungry, but
how do we go about translating optical and non-optical images of radio waves, ultraviolet light, infrared, into optical images?
They're with, coinciding. For example, if we want to show you infrared image, then those long waves of infrared will coincide with some red color, for example, with long waves of optical light. So they just make, these waves coincide with others in order to make the image and in order to see the shape, in fact, of some object. But we cannot see the image exactly, of course, we cannot. We just get some signal, electric signal, and so on and so on. We have computers now. For example, we use Fourier transformations in radio telescopes. But it is, these images are made in order to see the shapes of the objects.
We have time for one more question.
So you showed us some pictures of the sun, like the layers. How do you know how is the sun inside? Like we can't even go near it.
Well, yes, we cannot directly see that. We cannot directly. We can estimate that. We can do models. For example, like I said, directly we only get the electromagnetic spectrum. But there is one very important part of astrophysics that we call theoretical astrophysics. So we make models of the stellar interior. We solve, in fact, some equations in order to see what are the properties of the matters inside. Also, we do some other calculations, very complex, in order to see what are the conditions in the atmospheres where the absorption lines are formed. And what we get some analytical spectrum. And then that spectrum is compared with the spectrum that we directly got from the stars. And then we do that until we manage to get exactly the same spectrum like the ones we get from telescopes and instruments. So that is a part of theoretical astrophysics, and of course we use some physics laws, all laws of atomic physics, nuclear physics, and so on and so on, that were discovered in different ways, not in the stars. That's it.
Thank you, Dr. Kuzmanos.
Thank you.
Now it's lunchtime. After the lunch, we're going to switch the rooms. So the ones that were here yesterday will go to the library and vice versa. Is that clear? Okay. Have a nice lunch.